Okay, can you hear me?
Yes, I can hear you.
So, any questions? Okay, so here I will go to the chapter 12. This is a really important chapter because it really gives you the structure, general structure of semi-simple algebras. No? I mean, we have seen SU2 and SU3, and you'll see that those are, particularly SU3, the structures that we found are not accidental. No, this is a general feature for all semi-simple. So this is a kind of so we'll develop the whole structure step by step through many, many theorems. So we'll go through that, and then I hope to finish today at 12, because otherwise there are only 2 more lectures. So yeah. So yesterday, at the end, we defined already what was a definition of semi-simple algebra and semi-simple algebra, and there were some theorems about it. That every semi-simple algebra can be expressed as direct sums of simple algebras. So it is enough to study simple algebras, really, because once you know simple algebras, then you know everything about semi-simple algebra also. And also that the semi-simple algebra, there were 2 possible definitions. We use a definition that Cartan killing form is non-degenerate, right? But equivalently, the another definition is that it has no abelian invariant subalgebra. So that these are the 2 equivalent definitions. Okay. Now, just one comment before we start is that, like we saw before already for SU3, because we'll be looking at the eigen states, eigenvalues of the Cartan generators, right? So we'll have to complexify. So what we'll do is that we are just considering complex. So we are going to allow complex numbers to multiply all the generators. So it's a complex thing. And then at the end, we'll take the real parts. So in the intermediate step, since we are going to talk about eigenfunctions, you necessarily have to go through the complexification. So that's one. Finally, the Cartan subalgebra is, of course, a set of maximally commuting, mutually commuting generators. But there is one, the technical point, and that is so Cartan subalgebra is that, so first of all, there is a definition of regular element. Regular. So a regular element, so let's call it H. Suppose H belonging to the V. V is a full Lie algebra. So a regular element of H is defined as something that says that add of H has minimum number of 0. Of 0 eigenvalues. Okay. So this is the definition of LH. And then Cartan subalgebra is defined as a set of maximally commuting, maximal set of commuting, mutually commuting generators. Now that's the catch here, which contains a regular element. Not all the elements inside this Cartan subalgebra will be regular, but the condition is that it should contain at least one. So the regular, this is just to avoid some, because you see for SU2, SU3 we had explicitly the matrices and we could immediately construct the Cartan generators. But now here we are dealing completely abstractly. No? These are all generators as abstract, there's no matrices, nothing. There's some algebra is given, we satisfy the Jacobi identity. No? That's all. So we need to make sure that we are choosing a reasonable Cartan generators algebra. To give you an example, let's say in the SU2, SU3 case. So for example, if H1 has only two states, has only two zero eigenvalues, right? Because H1 with H2, I mean H1 with H1 and H2 of course is commutes. So either H1 or H2 it of course commutes, but H1 did not commute with X alpha 1 or X alpha 2. It didn't commute either of them, right? And also alpha 3. So alpha 1, H1, alpha 3. It didn't commute. So this was not 0. Okay. So therefore, it has only, and of course plus or minus, both, plus minus, plus minus, plus minus. So with 6 of them, it was giving non-zero eigenvalue. When I say 0, these were eigenstates and it was non-zero eigenvalues, correct? So H1 has only 2 zero eigenvalues. On the other hand, if you had chosen lambda 8, so H1 is a regular element, but lambda 8 is not, because lambda 8, it is 1, 1, minus 1, right? Up to some 1 over root 3 or whatever, minus 2. So this will commute, of course this will commutes with lambda 8 commutes with H1, H2, basically all the Cartan generators, and also it will commute with alpha 1, X alpha 1, right? Because lambda 8 commutator or lambda 8, the X plus minus alpha is equal to 0, right? So, I mean, remember X plus minus alpha 1 was basically this here, 0, 1, 0. This was for the plus alpha 1, minus alpha 1 was just a transpose of that. And this commutes because in this 2 by 2 block, this identity. No? This 2 by 2 block is an identity. So it will commute. So lambda 8 is not a regular element. Another example is if you take X alpha, let's see, if I take X alpha 1, X alpha 1 will commute with the, so what it will commute? It will commute with X alpha 1 itself, of course. It will commute with X alpha 3, right? Because remember, the root diagram is something like this, alpha 1, alpha 2, and alpha 3. The commutator of alpha 1, alpha 3 would be there, the sum of these two, but that doesn't exist. So X alpha 1 commutes with X alpha 3. And it also commutes with the, so plus minus alpha 3, it commutes with plus alpha 3. And also it will commute with X minus alpha 2. X minus alpha 2 is here. So X minus alpha 2. And it will commute with lambda 8. Okay. So it will have 4 zero eigenvalues. So therefore this is not a regular element. For example, I mean, I could have chosen, I mean, if it was just a question of maximally commuting generators, we could have chosen X alpha 1 and lambda 8 to define a Cartan subalgebra, right? But that will not be a good Cartan subalgebra. That's it. X alpha 1, you cannot find eigenstates for that. X alpha 1 moves. So that is why, because, okay, as I said, for SU3 it was natural. I mean, we have diagonal generators, just take that as a Cartan generator. So we never worried about these issues. But now we are talking in general, so we need to be a bit careful about it. Okay? So there will be a regular element. So at least it should contain a regular element. That's the point. Anyway, so this is just a side, I mean, it's not too important, but okay, just to clarify that there is a little bit of a subtlety in choosing your Cartan subalgebra. Okay. So now the various theorems. So now the next step will be to develop systematically various, understand the structure of the algebra. So it's a step by step, we will go through it. So the theorem 12.3. So the first statement is, so I have chosen, I will define, so this is the notation now. G is the complexified Lie algebra, the full Lie algebra. And we'll denote by H the kata. So at this point, even H is complexified because we have said already from the beginning we are talking about all complex. We have complexified everything. So even the H is complexified. Okay. Now the first statement is the full G is equal to H plus the various eigenstates. So let's say I call it G alpha summed over alpha. Alpha belonging to delta. That's the first statement. So again, so what is the idea here? So we take H and find, so each element, say, so any element H with some x alpha is some alpha H x alpha. So what we do is we take all the remaining generators from G and try to find the eigenstates, eigenvectors of with respect to all the H's. So H is an arbitrary element. So H is for all H belonging to H. So they are simultaneous eigenstates. So these x alphas are simultaneous eigenstates of all the generators of Cartman algebra. So like in the SU3 case, we had H1, H2 is the basis for the Cartman algebra. So what we are saying is that we are looking for eigenstates which are eigenstates with respect to both H1 and H2. Because if you ensure it is eigenstate with respect to H1 and H2, then it's eigenstate with respect to any linear combination. So that's so we just find all these eigenstates, and this statement is simply saying that the original Lie algebra, I can write it as the Cartman subalgebra plus for each root alpha. This is as usual the root. Alpha is the root. We call them a root. So the sum over all eigenvalues, roots, and the space and the vectors x alpha belong to G alpha. So G alpha consists of these eigenstates. G alpha is generated by all the possible eigenstates. In the SU3 case, we saw that for a given root, there was only one eigenstate. One linearly independent eigenstate, because of course you can multiply by any number, it doesn't matter, no? But it was all one dimensional. So in SU3 case, all the G alphas were one dimensional. But now we don't know, so, but we prove it. We prove that this is going to be one dimensional. Okay? But at this stage we don't know. This could be higher dimensional. There could be degeneracies here. There could be several x's, linearly independent x alphas which may have the same root. We don't know about that, right? So anyway, so G alpha will be all the x alphas which have the same root, okay, that will generate the G alpha vector space. It could be more than one dimension as far as we know. But also the only statement here is that G can be written as the sums of all of these vector spaces. Okay. So this is a vector space. That's for each alpha it's a vector space, and the full G can be written as that. But that's essentially a trivial statement because, I mean, after all the elements of H are commuting with each other, no? So we can simultaneously diagonalize them. Okay? So therefore, there are simultaneous eigenfunctions, eigenstates, okay? And those eigenstates, I call them, I mean, they belong to G alpha. So, no. So H's are there, and then take all the remaining parts of G, which are not inside the H, no? And look for all possible eigenstates, right? with respect to all the generators of Cartan. And this is possible because they're commuting. If this was not commuting, if it was not a commute, it was not an abelian algebra, then of course not possible, right? You know from your quantum mechanics course that if I have two operators which do not commute, you cannot find simultaneous eigenstates, right? For example, let's say the angular momentum along the first direction and angular momentum along the third direction, they don't commute. So you can't find eigenvalues of both third direction angular momentum and first simultaneously. You cannot do that. So that's just the statement of that. So since they commute, I can find simultaneous eigenstates and therefore, okay. So this was fine. Then the second, so this was the first one. The second one is, which we have seen many, many times, that if alpha and beta belong to delta, okay, then if I take any, so G alpha, so I will just write it as G alpha, because we don't know whether it's one-dimensional or not. G alpha and say G beta. So what this notation means, take any element of G alpha, this space, and take any element of G beta, and take the commutator. Then we know whatever it is going to be inside G alpha plus beta. This just follows from Jacobi identity, right? Because, Jacobi identity is still true. So H commuted, if I take any element, X alpha in G alpha and X beta in G beta, so we are asking the question, what is this, first of all, is it an eigenstate? And if so, what is the eigenstate of H? And if so, what is the eigenvalue? And then use a Jacobi identity that it says is the same as H X alpha, X beta, plus, this we have seen many times. Okay. So this is Jacobi identity. This result, this equation is from Jacobi. And then this tells you is alpha H, commuted with X alpha X beta. And this one tells you X alpha with the alpha beta, beta H, X beta. And since beta is a number, I can take it out. So this is plus. So it just becomes alpha plus beta H. So that's fine. Right? This you can just add that up. It's alpha H plus beta H times this eigenstate. So this will have, so the commutator will have eigenvalue which will have the root alpha plus beta. That's just a statement. This we have seen many times. Now, the third one. Shall I erase this part? I can erase this, right? Third statement is that if alpha beta belong to delta, delta is a set of roots. So the delta is a set of all roots. If alpha beta belongs to delta, and alpha plus beta is not equal to 0, then B is the killing form, Cartan killing form. So B is the Cartan killing form. This is the same thing, notation we have used, Cartan killing form. So the statement is that if this is the case, if this is not 0, then B of G alpha, G beta equal to 0. Okay. Now this is again this notation means that any element of G alpha here and any element of G beta here, if I take and compute the Cartan killing form for that, it is 0. Okay. So this. Again, we have seen this in SU3. B of X alpha 1 with X alpha 2 was 0, right? Because alpha plus beta is not equal to 0. Okay. So the proof is simply that, so what was the definition of B? B of x, say x alpha, x beta, I've just taken any arbitrary element of this. This is the same as trace add x alpha, add x beta. Right. Now, add x, so now let's take it, so let's look at the action of this add x alpha, x add x beta on an arbitrary element of the Lie algebra. An arbitrary element. So it could be, so I can ask the question, what happens if, for example, add x beta acts on x gamma, where x gamma is an element of g gamma, the root being equal to gamma. Well, this we already know. This is going to be inside, this will be some x beta plus gamma, right, from this here. Because this is just the commutator, this is the commutator, add x beta x gamma is the commutator of x beta x gamma. And from the previous statement we know, if I take the commutator of x beta and x gamma, whatever I'm going to get will be in beta plus gamma. No? So that's that. And now I apply add x alpha on this state, on this object. But this object was in x beta plus gamma, so in beta plus gamma. So this is going to be something which will be in x alpha plus beta plus gamma. Right? This is going to be some x alpha plus beta plus gamma. No? Because it just, this way, the roots keep adding up every time you take commutator. When you took this commutator, x beta with x gamma, you got x beta plus gamma. Now I apply add x alpha on x beta plus gamma, then it's a commutator of x alpha with x beta plus gamma. And what it's going to be, it will have a root which will be alpha plus beta plus gamma. Okay? So if you look at this operator, what it does, it takes, so this operator takes x gamma to, so when I apply this operator, it takes you to x alpha plus beta plus gamma. Okay? But trace means to take the diagonal elements, right? If alpha plus beta is not 0, then this is not the same as that. Okay? X gamma, gamma is different from alpha plus beta plus gamma, if alpha plus beta is not 0. If alpha plus beta is 0, okay, then there is no problem. But here we are looking at a situation where alpha plus beta is not equal to 0. Okay? So in that case, this is different from that. So this is off diagonal. You see, it is taking x gamma to x something else. You see, it is not bringing you back to x gamma. When you take the trace, the only thing which is relevant is when some operator takes x gamma to x gamma itself, because that is the diagonal element. Right? Think about it. If I want to write it as a matrix, so let's say I choose the kata here, okay, this part, then I choose x gamma, and then I choose say x alpha, x beta, and x alpha plus beta plus gamma. Okay, these are different, right? Because these are different because alpha plus beta is not 0. Okay, so now if you look at this, how can I write this matrix? It is going to be, so I have this here, so if I write it like this, so just focus on this part. So 1, 2, 3, 4, 5 here. So I should also draw 1, 2, 3, 4, 5, right? So this guy, this thing is going to be this operator. You see, takes x gamma to x alpha plus beta plus gamma. So that means it is going to be just this part here, right? This one. This one will be non-zero here. Some non-zero term. Okay, and everything else will be 0. So let me just focus on these two parts. So if you look at this part and this part, here this is 0, this is 0, and this is 0. And there are no diagonal parts here. Because this is not taking x gamma to karta or this and this, it is taking to that. So you have this one here. Okay? But when you take the trace, it's the diagonal part. So this trace is 0. Okay? So whenever you see the trace, the meaning is the same, that if you take this operator and see how it acts on various states. If it does not bring you back to the same state, then it cannot contribute to the trace is 0. Okay? Because that will not be a diagonal element. Okay? So that's and of course this is also true for even if I take, I mean this is for all, here I discussed for gamma non-zero root, but even if I choose gamma equal to 0, which means gamma equal to 0 means it's a Cartan subspace, right? This is a Cartan generator. I mean gamma equal to 0 is the Cartan here. What we said here. G, this one I will call G0. Sometimes I will just call it G0. Okay. 0 means it has 0 root, which means it commutes with all, it has 0 eigenvalue. Okay. So for gamma equal to 0 is nothing else but G0, which is H. So if you take H, then this operator will take you to X alpha plus beta. Okay. Again, it's not diagonal. If alpha plus beta is not 0. Okay. So therefore, we are saying that this is 0 because the trace is 0 and trace is the B. So this is 0. So any time, yeah. So the only way this may be non-zero is if beta is equal to minus alpha. You see, because then this will be 0. Alpha minus alpha would be 0, right? In that case, we cannot say anything about this. This argument doesn't work, right? Because then, if alpha plus beta was 0, this is mapping x gamma to x gamma. Okay, so then it is possible. But what we are at the moment, what we are saying is that if this is the case, then this is 0. That was basically the third point. Okay. Now the next one. So now this next fourth point is if I restrict B so if I restrict B to H, so both elements are, I restrict myself to when both are in the H, both the elements are in H, then this restriction is non-degenerate. Remember, right from the beginning, we are saying that we are discussing semi-simple algebras. So the whole of B is non-degenerate. Okay? The whole of B is non-degenerate. But if you now look at B, I mean, one way to think, I mean, a very quick way of thinking about it is, again, let's choose this basis, H, here. So this part is H, and here is all the other roots, non-zero roots, X, alpha, X, beta, etc., etc. These are all non-zero roots. Now, and similarly here is H and X alpha and X beta, etc. Okay. So we already said here, if I now specialize to the case, so if I take any B of H with any G alpha, where alpha is not 0, so alpha is a non-zero root, then this statement tells you that this is equal to 0. Right? Yeah, I mean, I'm just saying that if you take beta equal to 0, okay, then this is nothing else but the Cartan generator, Cartan subalgebra. But when beta equal to 0, certainly if alpha is not 0, alpha plus 0 is not equal to 0. Right? So this is all 0. So if I look at, so the way this will the B, so this I'm writing the matrix for B. Okay, matrix again in this choice of basis. So we are saying all of these guys will be 0, whatever x, gamma, and so on. No? They all will be 0. So this means it's B of H with B of X alpha with H. This is B of H with X alpha, but B is symmetric, so this is going to be symmetric, right? So all of these entries are 0. Only possible non-zero entry here will be this one. And possibly the remaining ones. But the point here is that when I say B is non-degenerate, which means that means determinant of B is not equal to 0. Okay? But since this matrix is factorized, there is this part and then the remaining part here, but with all of them 0, this determinant is nothing else but the determinant of this times the determinant of the remaining part. Okay? So if the full determinant is not equal to 0, then this determinant cannot be 0. And of course also this determinant cannot be 0. But at the moment we are just saying this is non-degenerate. So if I restrict my B to be, so I just look at this part, here, then this itself is non-degenerate. The determinant of this cannot be 0. So that was that. Yeah. Right? I mean, so. And then the fifth one is, any question by the way here? No? Okay. The fifth one is if, so this is the fifth point, if alpha belongs to delta, okay, and I'm taking alpha not equal to 0, so a non-zero root, then this implies that minus alpha also belongs to delta. We saw it, of course, in SU3, SU2 we saw, SU3 we saw we have x alpha 1, x minus alpha 1, no? But now we are asking general question. Can I generally say that it must be so? That this alpha exists means minus alpha also exists. And the answer is again comes from here. You see, if suppose minus alpha did not exist, then we are saying that B of x alpha, where x alpha belongs to G alpha, take any x alpha inside the G alpha. This is with anything, so it is 0 with H, of course. Alpha is non-zero root, so this is 0. And B x alpha with everything else, x beta, everything is also 0. Okay. Since, I mean, this would be non-zero only if beta was equal to minus alpha. But if minus alpha did not exist, then this would be a 0. Right? That would mean that again in this column now, see, everything is 0 here. I mean, this is 0, this is 0, this is 0, this is 0, etc. If minus alpha did not exist. If one of these guys, beta or gamma or minus alpha, then that will be non-zero. That may or may not be 0, but at least, I know that all the remaining ones, if beta, so this is a true statement, if beta, gamma, etc. are not equal to minus alpha, none of these are equal to minus alpha, okay, then this whole thing will be 0. Then the determinant will be 0. Right? So therefore it implies, since we are dealing with a semi-simple algebra, since B is non-degenerate, therefore we are guaranteed that minus alpha must also exist. So again, you see how powerful it is, just demanding a simple thing, that Cartan metric, Cartan filling form is non-degenerate. We are getting all these results for free. I mean, all these statements for free. So that's the thing here. Okay, now the last part, it's always good, good to think in terms of this matrix, because that you immediately see it. You immediately see the proof of the theorems, various theorems. Also for the computation of this adjoint, even to compute the add B, the B itself, add actions and so on. It is useful to think in terms of it. Okay. The last point. Now the thing is that, okay, so we have now all these alphas, right? Or we wrote down this. So we wrote down G. The full G was H, which sometimes we'll call it as G0. plus G alpha. Alpha belong to the roots. So these are non-zero roots. So we said, okay, for every alpha in this set, in this delta, if alpha exists, then minus alpha also exists, right? Because that was the previous conclusion. But how do we know whether, okay, we already saw alphas are all roots are in the belonging to the dual lattice, H star. Dual kata, dual lattice, dual of the kata. But how do we know that that this set of alphas span H star? It could be that all of these alphas, so let's say H was, okay, in SU3 case, H was two-dimensional. Let's say in some general, something which is, this is n-dimensional. Some general algebra. Now, so if this is n-dimensional, H star is also n-dimensional, right? The dual vector space has the same dimension as the original vector space. So, okay, we have a lot of alphas, but it could be that all of these alphas are sitting inside some subspace. It's not in the full n-dimensional space, but perhaps, let's say, n-1 dimensional space, right? That would mean that even if I take all the linear combinations of alpha with arbitrary coefficients, I will not be able to span the entire H star. So the statement now here, so what we are saying is that alpha belong to the set of, so alpha belong to delta actually spans H star. Now, what does it mean to say that? So this is the statement. We want to prove that. If you assume semi-simple algebras, then this will happen. So to prove that, what is the meaning of this statement? Let's see. So when we are saying alpha does not span H star, okay? So it is some. So that means that this would imply. So assume the contrary. So suppose alpha doesn't span. Does not span H star. Okay. Then there must exist some H belonging to H, the original Cartman generated subalgebra, such that alpha H equal to 0 for all alpha in delta. Because you see that, as we said, I mean, I don't know if you are you convinced by that? Because if you are saying that alpha doesn't span H star, so there should be some element, some dimension. So as I said, suppose H was n-dimensional, H star is n-dimensional, right? So if it doesn't span full H star, maybe it spans n-1 dimensional or n-2 dimensional, but some directions are not spanned at all. Okay? Now, the reason why H star and H have the same dimension is because this was the set of all linear functions on H, right? It was a set of all linear functions on H, which maps H to numbers. Okay? So if H is n-dimensional, H star must also be n-dimensional, okay? Because you can just choose a basis. I mean, suppose I choose a basis, let's say EI are the basis of H. Basis of H or any, I mean, this is not even, nothing to do with any Lie algebras. This is a question of vector space, even before talking about the Lie algebra. This is an issue of vector space. Then H star are all linear functions. So I can define my, let me choose a basis here, in a constructive way. So let's suppose I choose EI, so upper index now, yeah? Upper index is an element of H star, so which means it's a linear functions on all this. So I define it like this, Eij is equal to delta Ij. This is a linear function. Now I have defined it on the basis, but it's also clear that any element of the H will be generally some xj, Ej, right? This will be an arbitrary element of H. So how this EI acts on that? So EI acts on sum over xj, ej. Since it's a linear function, so I can take it out, take out these numbers out. This is the same as sum j xj EI acting on ej. That's the delta ij. And so therefore this is nothing else. This is nothing else but xi. So EI acting on xi. Right? So I have found this basis, and then any linear function I can express as a linear combination of these EIs. So then we are saying that any element of H star, so any element, let's say some f, f belongs to H star. Well, f belongs to H star, I can define this by just specifying the action of f on all the basis vectors, right? Ej, let's say. Well, if this will be some numbers, f of j, okay? This defines to you uniquely what this f is, because again by linearity, then you know how f acts on an arbitrary element here via these similar techniques. Okay? So now, so a question now is, can I write this f in terms of this basis EI? And the answer is yes. You can write f. This f is nothing else but fj ej summed over j. Just try it out. You try it out. If you, I mean, sorry, is there any question? I mean, what is the logic? I'm just trying to say, why did we say that the H star has the same dimension as the H? When we are defining H star as a dual vector space, which means it is the space of linear functions, functions on H. So which means, what is a function? Function means it's a map from the H to numbers. Huh? So this is the way one proves actually that H star and H have the same dimension. Okay. I mean, this is one of the ways of proving it explicitly by choosing a basis. So what we are saying that if alpha, now is that clear, or because so what I'm saying is that so let's suppose I look at this alpha and say alpha does not span all H star. So for example, in this you see the basis for, we are saying the basis for H star, so H star basis is spanned by this EJs, j equal to 1 to n, if it's n dimensional. So if we say that alpha does not span all H star, it's some lower dimensional, so it's not n dimensional, it spans some lower dimensionals, let's suppose n minus 1 dimensional, okay? And so in that n minus 1 dimensional, say j equal to n is missing. We have only E1 up to En minus 1. There's one extra direction. Say that En is missing. If so, if En is missing, so let's suppose En is missing. Or it could be any combination, but just for simplicity, let's suppose En is missing. So alphas do not span En. Any combination of alpha does not give you En. It gives you all the remaining ones, but does not give you En. Okay? If so, then you see this, then alpha acting on En, now in the original, this is the basis on the original, is always going to be equal to 0. Because we are saying that alpha is a combination of all the remaining ones, Ej with arbitrary numbers, Fj, sum over j, but j goes from 1 to n minus 1. Okay. And if you act that on any, on the En, if you act on this on the En, it is 0. Because this does not include n. Okay. Right? I mean, if this acts, so if alpha acts on Ej, or Ej, it will give you so it will give you, if it acts on j, where j is between 1 and n minus 1, okay, it will simply give you fj. Because they say this is k, Ej is simply delta kj, right? So, okay. But if it acts on the En, it is 0. Okay. all the alphas, because we are saying that alphas, this is the spanning, no? All the alphas, they do not, even any linear combination of alphas does not give you En. Okay. Then that means going back to the original, so this is the dual vector space, but then going back to the original vector space, it says there must exist some element in the original vector space, meaning H, such that alpha H equal to 0 for all alpha. So that's the argument here. But if so, if this is the case, so we want to prove a contradiction. So we assume that alpha does not span all stuff. This would imply this, but then we want to prove that this cannot happen. No? So what is the reason for that? Okay. The reason is that we already saw that if you take B, if you take the Cartan-Killing form between two arbitrary elements of H, H and K, okay, I hope this will not get confusing. When I talk about the vector space, I will always use a script, I mean this kind of curly thing. These are just elements. Okay. So B of HK was, remember, it was simply the sum over all roots of alpha H, alpha K. Right? So we are saying now that there is, I mean, this is arbitrary H, but now take arbitrary H and K. But now let's take this particular H such that all the alpha H is equal to 0. No? In that case, this is going to be equal to all 0, right? Because there's alpha H sitting here, and we are saying all the alpha H, for all the alphas, alpha H is 0. So this is 0. That means B of K is completely arbitrary. K is completely arbitrary. We are only fixed one element here, H. K is completely, so for all K belonging to H, this is always 0. If I choose this particular H, for which alpha H is 0. But then, we already said in the very first statement, or second statement, second theorem, was that B restricted to the Cartan was non-degenerate. But if such an H exists, such that its inner product with all the elements of the set is 0, that means it's degenerate. Okay? So this would imply that B restricted to the Cartan is degenerate. But that we already know is not true, is not possible, right? So this proves a contradiction in this. So therefore, we conclude that alpha spans all the H star.
Please, Professor, the last line, for every H belongs to H is equal to 0. So how does this imply that the determinant of P is equal to 0?
I mean, this is the basic statement. When when you say a matrix is, the determinant of the matrix is 0 or not 0, if the determinant is not 0, then the statement is that if dit of B is not equal to 0, no? That means it's invertible, then that means that there is no H which is not equal to 0 itself. Of course, if H is 0, then it is trivially true. But no non-zero H, there is no H which is not equal to 0, such that B of HK is equal to 0 for all K. That's actually the statement. I mean, one way to realize this is that just write in the matrix, that matrix language. No? So let's suppose this BH. So choose a basis such that, choose a basis for the V algebra now. I'm just choosing a basis for H, for the Lie algebra, for the Cartan algebra. So choose this H as one of them, this particular H, for which all the alpha is equal to 0. And then all the remaining ones. I don't know, let's say H H1, H2, up to Hn minus 1, right? So this is, say, n-dimensional. So we choose a basis such that one of them I take it to be just that H. And then the remaining n minus 1. These are, of course, linearly independent, right? The basis always has to be linearly independent. Now, choose this basis. So again, here H and H1, etc. So we have this matrix here. And let's look at the entries of this. Okay. We are saying that B of HK, so this is a matrix B. I'm writing the matrix B in this basis. We said that B of HK is 0, but K is arbitrary. That means this whole row is 0, and all of this column is 0, because anyway, B is symmetric. So the determinant is 0, right? The determinant will be, this may be non-zero, this part is non-zero, but you have 1 0 row or 1 0 column, so its determinant is 0. That's the statement here.
Professor, in that case, when we said that alpha of this particular H is 0, this is up to a particular basis, right? Because
This is the
up to a particular basis that we choose, or why don't we say that this alpha of H is a linear combination of all the other H's?
But that is fine. You can. This is independent of choice of basis. Right? So let's see. Okay. So let's say I choose some basis. Say choose some basis for that. So choose a basis. Say EI, basis for the H. And this, our little H may be some particular combination xi, EI. And we are saying that so this object is, so now let's look at B of H with all the bases, EK. So I take this. Well, this is, okay, so why is it 0? That was 0 because of the simple reason that we already know. This is nothing else but alpha H, alpha EK, summed over alpha. But if alpha H is 0, then that is 0. Huh? So we see that B of H of EK is 0 for all K. For all K. K going from 1 to n, say, is n-dimensional. Okay. But that means B, so actually this already says that this says it's degenerate already. But if you want to think in terms of the matrix, that's nothing else but we are saying B of X, so substitute this here, B of Xi, EI, EK equal to 0, summed over I here, for all K. Okay. So now I have the matrix here B, so this is nothing else but Bik in this basis, no? So we say, so this is E1 up to Ek, E1 to Ek, and these entries are, so this is B, E1, Ek, E1, and so on. Right? So I put this entry. So this is my B matrix. So when I say this combination is 0, so what are we saying? We are saying that there is a certain combination of these rows which gives you 0. This is 0 for all K. But you remember when you take the determinant, this is what you do. This is one of the allowed operations, right? You can just take any linear combinations of these guys and substitute here this row with a linear combination of them. That doesn't alter the determinant, no? So what I'm saying, now take the linear combination. Choose X, suppose X, one of these X's is not equal to 0. Not equal to 0, at least one of the X is not equal, Xi is not equal to 0. Normalize it, divide by that Xi, so that is 1. Okay? So let's say X3 is equal to some non-zero number, at least. There are probably several non-zero numbers, but say X3 is not zero number. Then I put X3, just divide by X3, okay? And then you take the combinations, just divide this equation by X3, but doesn't matter. So then you take the linear combinations of all the remaining guys, which are dictated by those coefficients. So x1 E1 plus x2 E2. So x1 times the first row, x2 times second row, x3 times third row, etc. Okay, and add that all to the third row. So x1 times this, x2 times that, x4 times that, fourth row, etc. Add that to the third row. Multiply third row by x3 and add that. Then the third row becomes entirely 0. So this is a general statement. Or another way to say is that, so what are we saying? We are saying that this, so this is equal to 0. So think of this as, I mean, okay, let me put here like that. This is symmetric anyway, so it doesn't matter. No? So this equation, I mean, if I write these guys as a matrix, this is a n by n matrix, Ki, K is the row and I is the column, okay? Where the entries are, so entries are B, I mean, in the kth row, this is the kth row and the ith column. What is the entry? It is B, E, K, E, I. This is the number. So this is the matrix. Now if I look at this equation, it is nothing else but this equation. x1, x2, up to xk, up to xn. This is equal to 0, 0, 0, 0. Okay. That's the equation, right? I mean, we are saying that this implies this equation. Okay? Because this has to be true for every k. So for every column, this must be true. The right-hand side is 0. So that's why I have a matrix equation. Okay? Now, if I have this matrix equation, then there's no solution if the determinant is not 0. Right? There's no solution to that. The only solution is if all of them are 0. But that cannot be because we are taking this h, so which is some non-zero element of original h, right? Such that this is all 0. So certainly not all x's are 0, right? So we are saying, where is that? I wrote, yeah, so we said h was some combination xi, ei. Okay? Since h is not 0, that means not all xi's are 0. I mean, some of them may be 0, but not all of them. No? So this is a non-zero column vector. Right-hand side is a 0 column vector. If this determinant was not 0, then I can invert it. Okay? Then this column will be the B inverse acting on that, but that would be 0. You see? So the fact that we have a non-zero solution here to this equation, it implies that this B is not invertible. Okay? Which is a contradiction because we know that this is invertible. So that is a way to show that such an H does not exist. No? So you see, it's a yeah. So this is the way of proving. I mean, this is many times this method is used by contradiction, proving by contradiction. You assume the contrary, and you say that you arrive at some absurd conclusion. You know? So therefore, original assumption was wrong. Okay, so this was, so where are we? You finish all that, first thing? Yeah, so that's that. Okay, so the theorem 12.3 we finished. Any question? So this is, you see, step by step we are trying to figure out more and more the structure of the algebra, right? I mean, all of these things we have seen in SU3, right? I mean, that these are all true in SU3, but now what we're saying is in general. Okay. Because in SU3 indeed the roots, non-zero roots spanned the H star. No? H star was two-dimensional and the roots that we drew, they were two-dimensional. They were spanning, they were not all parallel to each other, not one-dimensional. Now let's go to the next step. Okay. So okay, now yeah. So there's a definition here. This we have again seen the definition before, but again just to remind you. So remember that given a root alpha, we associated, so this was in H star. We associated an element in H, which we called H alpha, right? In H. This we did before, yesterday, but I don't know, last week. So the way that definition was simply this. It was using the Cartan-Killing form. B of alpha, H alpha k, is equal to alpha k for all H, or all k belonging to H. So that was the definition, which we already discussed before. So this is a map from H star to H. We associate a particular element. Okay. Yeah. So now theorem 12.4. So this is a very important point. 1. X alpha, X minus alpha, the commutator of. So we already seen the previous theorem that if alpha exists, then minus alpha also exists. The root, right, that we already saw. It was the number 5 or the last theorem. If alpha belongs to delta, minus alpha also belongs to delta. So we can ask the question: what happens? What is this commutator? X alpha with X minus alpha. And the answer is that the statement is that this is simply B of X alpha, X minus alpha times H alpha. H alpha is this particular alpha, which is this map, defined through this equation. So that's. You see, even this H alpha, the reason why H alpha is defined uniquely through this equation was again from that matrix equation we wrote down. Choose a basis, and then given this information, so the right hand side now is not a zero column vector, it is something. No? Then you can find those coefficients x's. You see H alpha, you can choose a basis. H alpha, I can write it as some coefficient which we don't know yet, xj, ej, right? xj, ej was some basis. And then you can write everything in terms of that basis. Then here it will be some non-zero column vector, and x's are unknown, so this will be a column vector, and then this will be an n by n matrix. Okay? And so the reason why these x's are determined uniquely is because the B is invertible, so that you can find the inverse, you can apply the inverse there. No? So this is the basic, that's the reason why this uniquely defines, this equation, which is true for all k, uniquely identifies what is H alpha. There is a unique solution to this equation. Okay, so this is the first statement. And of course, so this was some element of what we were calling G alpha, and this is some element of G minus alpha. Okay, so the statement here we are saying is that this is in general true. It's not just for one of them and one of them, but in general this is true that G alpha, G minus alpha is equal to complex numbers, because we have complexified everything, times H alpha. No, it's not. It's curly. H alpha. Okay. This is just a statement that, we don't know, this may be more than one dimension. In SU3, these are all one dimensional. For each root, there was only one degeneracy was 1. But we don't know yet. So in principle, G alpha and G minus alpha could be higher dimensional, not just one dimensional. So here the statement is, as I pick one of them, then there must be existing some element here, such that this is equal to this. And then you take an arbitrary element here, an arbitrary element there, that is going to span. But this is always one dimensional. H alpha is one particular element of the Cartan. So one complex dimension. I mean, because now we have complexified everything. So when I'm saying one dimensional, I mean one complex dimension. So all complex dimension. That's the statement. So how do you prove that? So this is, for this we need to use something else, which is again a general property, you know, there's something you must have, I don't know if you saw that before, but if you take this definition, take an arbitrary x and take the commutator yz. X, y, z are arbitrary elements. X, y, z are arbitrary elements of, say, original G, the full G. So you take that. Then this is the same as B of x, y, z. Okay. And the way to prove it is simply use a cyclicity property of the trace. This is nothing else but trace add x with add y commutator of yz. Okay. But the commutator of add yz is nothing else but the commutator of add y with add z, right? So I can write this as a trace of add x and times the commutator of add y add z. Okay. But then I can open it up. There are two terms here. So trace of add x, add y, add z, minus the trace of add, or let me write in the same thing, minus the add x, add z, add y. Right? I mean, I just open this thing, open this bracket. But now what you do is you use a cyclicity. So leave that as it is, but this term, you move add y here by cyclicity. You move it. So I move that there. Nothing changes for the trace. And now you see add, both the terms add z is on the right hand side. So this is add x, add y, minus add y, add x. Whole thing times add z. But that's the same as trace of the commutator of add x with add y times add z. But that's the same as trace of add of commutator of xy with add z, which is the same as that. This is the same as that. So this is a very general property, the Kaplan property. This is one is just using cyclicity of the traces, nothing more. And the fact that this is a representation. I'm going from here to here. I've used the fact that the representation must preserve the commutator structure. No? That is what the statement, and similarly here. Okay. So using this then, we can do the following. We can write, so the first statement we want to prove is that, right? So we can, so let's look at that. Let's look at this expression. Can I erase this part now? Or this part is okay? So let's start from this expression, b of x alpha, x minus alpha, with an arbitrary element h. Okay. Anyway, this is going to be in a Cartan, so this is in Cartan anyway. So I just take a Cartan killing form between this commutator and that. But this, using the previous relation, is nothing else but b of x alpha and with a commutator of x minus alpha with h. Okay. Which is the same, I mean this commutator is nothing else but alpha h times x minus alpha, right? I mean, if you can just exchange the h with x minus alpha here, but this is a commutator, so you pick up a minus sign. But h with x minus alpha is minus alpha h. So that minus minus cancels plus. So plus alpha h times x minus alpha. So this is nothing else. So alpha h is a number, so I can take it out. So this is alpha h times b x alpha x minus alpha. Okay. That was the first point. But on the other hand, so again, alpha h is b of h alpha h, right? That was we defined this. This is the general definition. This with the dual. So the b, this is that, and then there's a b of x alpha x minus alpha. So from this, what do we conclude here? But now you see, this is just a this is a number, right? So I can rewrite this as b. I can put it inside here. So I can write this as b of bx alpha x minus alpha times h alpha comma h. I mean, think of this, start from there. This is a number. So b of a number times h alpha, comma h. Okay? B is linear, this b is linear, so I can take this number out. Then you get that. Okay? So it's just a way of writing it, this thing. But now I can compare directly this equation. So what we are saying here is that b of x alpha x minus alpha with any h is equal to this with any h. Okay. Therefore, for example, if I subtract that, so therefore this, if I bring it to the other side, this implies that b of commutator x alpha x minus alpha minus b x alpha x minus alpha times h alpha. This is take the inner product between this and h. This is equal to 0 for all h. All h belonging to the Kartha. Right? I just put it on the other side. I mean, this is equal to that, so I just subtract this minus that's equal to 0. And what I've done is both of them have h as one of the objects here, so that is h, and combine all the remaining ones. So this is x alpha x minus alpha commutator minus that guy. But this is true for all h. So that means, so I know of course this is in the Kartan, that is explicitly in the Kartan. So this is some Kartan element, and we are saying this Kartan element has 0 inner product with all the h's. Since b is non-degenerate, that implies this must be equal to 0. There's no other solution. Okay? And that proves this statement here. So the logic was that, so if this is true, then this minus that must be 0. This is the Karta, this is also in the Karta. This minus that must be 0. But if this is 0, then its inner product with arbitrary h must be 0. Right? It is if and only if. This minus that is equal to 0 if and only if the inner product of this minus that with any h is equal to 0. And what we have done is that we have proven that. So therefore we conclude that this is 0, and we will produce that equation. Now I want to stress this. Now let me see how much time I have. Okay. I wanted to at least finish. Okay, just wanted to remind you that you remember for SU3 case, what we had x alpha 1, x minus alpha 1 commutator was, okay, some number times h alpha 1. No? And the same thing with alpha 2 and alpha 3. They're all the same. Huh? And it looked like a kind of accident or something, but it happened. But what we are seeing is it's not an accident. This is always the case. You see. The commutator of x alpha, x minus alpha, this was, remember, this generated an SU2. X alpha, x minus alpha, and H alpha generates an SU2 subalgebra. Huh? But, so the commutator of, so the raising operator and the lowering operator, the commutator of that gives you the H alpha, I mean the third generator, but it is not some arbitrary element of the Cartan generator. It is that specific H alpha which is dual to alpha via this map, via this Cartan killing form. No? This map was coming from the Cartan killing form with this equation. So it is not some arbitrary H alpha which appears there, arbitrary element of the Cartan. What appears is exactly the one which is mapped to alpha via this map. No? So it's a completely general feature. So that, okay, now the next two statements, there again, the proof of it, they are very interesting again. Because from the proof you learn about the method of proof itself. Because we will be using the SU2 representations. Given the fact that this forms an SU2 algebra, it's an SU2 algebra, right? Because x alpha, x minus alpha is H alpha, and the commutator of H alpha with x alpha is going to give me some number times x alpha itself, right? The roots. It will be just alpha H alpha, x alpha. So with a plus or minus alpha, it's going to be plus or minus that. So this clearly these three things form an SU2 subalgebra. No? I mean, think of this as J plus, J minus, and J3. No? So this forms an SU2 subalgebra up to some normalization which you can absorb inside the definitions of the generators themselves. So that normalization is not important. Important is that these three form an SU2 subalgebra. So now we can use all our knowledge of SU2, just like we were using for SU3, the knowledge of SU2. No? So now we can do it for arbitrary. So the next two statements is so the first statement is that BH, so the next statement is BH alpha, H alpha, so alpha is some root, alpha belongs to the delta, okay, non-zero root, alpha not equal to 0. So this is not equal to 0. That's the statement. Now this is the proof of this will be it will be interesting. Okay. So the idea is, so okay, we know that I mean the B restricted to H is non-degenerate. This we know. Okay. So there must exist some H beta. Such that, so there must exist some H beta in H, H beta, such that B of H alpha, H beta is not equal to 0. Okay. Now, what is the reason for that? The reason is that we saw that alphas span the H star, right? All the roots, alphas span H star. Then H alphas will span H because this is a dual. So it will span H. So the fact that this is non-degenerate means that there must exist some H, at the moment let's say some H, such that B of H alpha, H is not equal to 0, right? There must exist some H. Right? It cannot be that for all H in in the Cartan, this is 0. If that cannot be, right? Because H alpha certainly is not a 0 element, it's a non-trivial element of the Cartan. So non-degeneracy means that there must exist some H in the Cartan subalgebra such that BH alpha H is not equal to 0. But that H I can always expand. Expand in terms of this H, I can expand in terms of write some combinations of H betas with the coefficients. Okay. Now, if it is true that if it happens that H alpha with every H beta is 0, then it will not be possible. This will be 0 identically. So this proves that there must exist some H beta such that this is not 0. Okay. So start from this beta. So we say that there exists some beta such that H beta, B of H alpha H beta is not 0. Okay. So now consider, so let's say, so we have the G beta. So we have this G beta corresponding to the beta root beta. That is the subspace of the full Lie algebra. Now what we are trying to do is to construct a representation of this SU2 algebra starting from this G beta. Okay. So what you do, we start applying X alpha. Okay. Then I'm going to go into G of beta plus alpha, because remember when I apply add X alpha on this, so this is all add X alpha. Add X alpha on this, I'm going to get something in the G of beta plus alpha. Right? The roots add up. No? And then keep going. So I'm just applying the raising operators. Just keep applying. I will drop this add. It's understood that, of course, we're talking about add representation, adjoint representation. So this X alpha takes you to G beta plus 2 alpha and so on. Okay. On the other hand, I can apply X minus alpha and I will go to G beta minus alpha and so on. Keep going. So we are constructing this SU2 representation, starting from G beta. Okay. This is what we are trying to do. So consider the entire space. Consider this V. V is the subspace of, remember now we changed the name. Now the Cartan subalgebra we are denoting by, no, not Cartan, the G, the full Lie algebra, we are denoting by G rather than V. Earlier lectures we were using this for the notation for the Lie algebra, but somehow the notation has changed in this section. This is the Lie algebra. Now the V is a subspace of G, which is given by simply the sum n of G beta plus n alpha. Okay? This is a vector space sum. So each of them is a vector spaces. You just take the direct sum of the vector spaces. And sum over all n. So n belongs to integer. All possible integer where this is not null. Of course, we know that in reality this is going to terminate somewhere, right? Because it cannot go on. Otherwise, because we are talking about finite dimensional spaces. So it won't terminate there, it's going to terminate here. But I just put the sum over, since I don't know where it terminates there, I just take all the sums for arbitrary integers such that this is not null. If it terminates means it is 0 dimensional, so we don't care about that. But consider this. Now the point about this is that this, if you look at this subspace, this V subspace, this SU2 generated by X alpha, X minus alpha, and H alpha, this SU2, this will be a representation of that SU2, right? May not be an irreducible representation, doesn't matter, but it's going to be a representation. Okay. Because the actions of these three generators, they will take a vector an element in this vector space back to again an element in this vector space. It's not going to take you out of it. No? Because by definition, action of X alpha takes you to this space to that space. No? And X minus alpha X takes you to that. X alpha here, acting on X alpha, you come back here. So this gives a representation of the SU2. may not be, as I said, may not be irreducible representation. But whatever it is a representation. Okay? Okay. So then in a representation, we can always talk about so we can then take the trace of add H alpha. So remember, all these actions were add. So I should really put add. So I mean, again, is that clear to you? X alpha moves you one step that way. Add X alpha. Add X minus alpha moves you one step this way. And what about the H alpha? The third generator, add H alpha. Add H alpha is just diagonal, right? Add H alpha takes a vector here and brings it back there. No? Up to some number. These are all eigenstates. So there will be some number times the same vector back. So all these three generators of this SU2 are keeping the states within the same. That's why I said this is a representation of the SU2. So now let's take add H alpha, but trace not over the full G, but trace over this V in the subspace, because it's a representation. So I can talk about the trace in just that subspace. No, it will be block form. If you look at the full add H alpha, there will be this space, then there will be some, let's say instead of beta, suppose I have a G gamma, there will be another space and so on and so forth. But I'm going to take the trace only over that, not the full G. Okay. But then add H alpha is so did I prove that? Let me see. Yeah, so just now use this thing here. So the point is that, okay, maybe I could have, no, let's do the following. Let's look at, maybe instead of starting from there, let's look at this object here. Let's take the trace over this commutator. Add X alpha, add X minus alpha. Commutator in this space. Okay. But that's 0, right? Because it's a commutator inside the trace, it is 0. Trace of a commutator is 0, right? Because it's just this times that minus this times that. But a cyclicity, you can move it, it's 0. So, but of course, for this to make sense, you should consider, this is important, that this should be in a space where, which is a representation of all this. I mean, if it had happened, suppose I had taken only some, not the full V, but only this part, okay, in the trace. Then you cannot use the cyclicity, etc. Because it is not closed. I mean, X alpha acting on this takes you out of this space. No? And similarly, X minus alpha takes you out of this space. Then you cannot use this thing that this trace of the commutator is 0. Okay? For this to work, it should be a space where I mean, the complete representation space where X alpha and X minus alpha are acting. Okay? So that's why we took the V. Okay. So this is equal to 0. So now it's perfectly okay. But then I use this property. So this is nothing else but V X alpha, X minus alpha is a number, and then trace of V, trace over V of add H alpha. So essentially, then from here we conclude that trace of V at H alpha is 0. But then we can compute already directly here, right? Because we know how the add H alpha acts. add H alpha acting on this G beta. So we want to look at how this H alpha acts. So H alpha acts on some X beta, G beta. That's going to be nothing else but beta H alpha G beta. Right? I mean, so take an X beta here. That's going to be this. So it's purely diagonal. So I can just take the trace over. This is a completely diagonal matrix. I can just sum it up. Sum up the trace, right? So the result will be this right here. So now we have to, what is V? V is nothing else but the sum over n of the trace over G beta plus n alpha of add H alpha. Well, this is nothing else but sum over n of when you have, so here if I take this any element inside this G beta plus n alpha, so that's going to give me this object, so beta H alpha plus n alpha H alpha times dimension of G beta plus n alpha. Right? Because remember, we still don't know the dimension is 1 or not. Right? So at the moment, we have no idea. This could be of any dimension. This space, each of these spaces can be of different dimensions. We don't know that. So I just take that number. This is some integer, a non-negative integer. Right? It could be 0 if the dimension is 0, but it cannot be negative because the dimension, counting dimension. So that's the formula here. Okay. But on the other hand, this trace is equal to 0. So what does it mean here? So this, if you look at this expression, yeah, we already said something here, H beta. Where this is not equal to 0, right? Now, if you look at this expression, what is that, this thing? This is nothing else by definition is B of H alpha H beta. And that one is plus n B of H alpha H alpha. Yeah, this was just, remember, that is how we defined the map, right? So let me write it like that. Anyway, it's symmetric, doesn't matter. So we said that beta, H beta is defined by this equation, right? I mean, you remember that? I mean, the way we defined the map from the root to this root to the corresponding element in the Lie algebra was by this equation. So the beta of H is equal to B H beta of H for all H. This was the definition of H beta. So what I'm saying is that I just use this equation. So beta, take this particular thing as H alpha. So that's nothing else but B of H beta H alpha. And the same thing here. So this times dimension times the dimension which is of beta plus n alpha. This whole thing is supposed to be equal to 0. Okay. So the conclusion, this we know on the other hand is not 0. That is the way we picked up the beta. So this is certainly not 0. So if suppose B H alpha was 0, then there is no way I can satisfy this equation. Because you have this something not 0, and these quantities are all positive. I mean non-negative. Yeah? And at least I know that for n equal to 0, the G beta, this exists. I mean, I've started from that. This beta exists, this root beta exists. So this certainly has dimension not equal to 0. This is 1, dimension 1 or 2 or whatever it is. So not all these numbers are 0. Okay? And this number is coming common to everything. So this is not 0. So there is no possibility to satisfy this equation unless this was not equal to 0. this was not equal to 0. Is this logic, I mean, reasonably clear? So what we are again, let me repeat that. So we said, in this representation B, this is a representation of SU2, add H alpha is nothing else but the commutator of these two. Trace of the commutator vanishes, so from that I conclude trace of the add H alpha must vanish. This is the same that we know for any SU2 representation. If you look at the J3 quantum numbers, for every positive eigenvalue there was a negative eigenvalue. So trace was 0, right? It went from J to minus J in units of 1. So for every n quantum number there was a minus n quantum number. So the trace was 0. So that's exactly that statement. We are just using SU2 structure. But now we compute explicitly, we know what the eigenvalues are. In this G beta plus n alpha space, its eigenvalue will be simply beta H alpha plus n alpha H alpha. Okay? That's the eigenvalue. I mean, is that, I mean, now this, I'm just using the old thing, that if I take an H, add H, so in other words, commutator of H with any x alpha was nothing else but alpha H x alpha. That's what I'm using, right? So now it's specialized to the case where H was H alpha. So this I use, okay, now specialized to case where this guy is replaced by x beta plus n alpha. So it's an element of the beta plus n alpha space. And this H, I just take it to be H alpha. Then what is it going to be? So alpha is replaced by beta plus n alpha. So it is beta plus n alpha. And then H is replaced by H alpha. So this is H alpha here, right? Times H alpha. That is what I'm saying. X not alpha, beta plus n alpha. So the add H alpha acting on this is this number times the same vector. Okay. And when so it's a diagonal element, so I take the trace over that, which means I have to sum over all this. Now, so that this expression is just that. This beta plus n alpha evaluated at H alpha. So since it's linear, so that is the same as beta of H alpha plus n alpha of H alpha. But these guys by definitions were those. Right? And this whole thing is multiplying the dimension of this space because this guy was just one of the elements of this space, G of beta plus n alpha. Okay? If suppose G beta plus n alpha was two-dimensional, not one-dimensional, then there will be two linearly independent such X beta plus n alphas. No? There will be two linearly independent such states which will have the same eigenvalue. In that case, the trace will give you a factor of 2 because it will be 2 by 2 matrix with the diagonal element being the same. So it will be 2 times, which is the dimension, 2 or whatever the dimension, times this. Okay. Now I know, for example, that at least one of the terms is certainly not 0. D of dimension of beta is certainly not 0 because that was my starting point. Okay, that there exists some H betas, there exists some beta. No? So certainly this dimension is not equal to 0. At least the dimension of this is 1. No? So d beta is certainly not 0. So at least there is one term which already gives you this non-zero term. No? Beta. There is no way to cancel it because left hand side is this is 0. The only way I can cancel it is if this guy is not 0. If this guy is 0, then there is no hope of cancelling it. So this proves that B of H alpha is not 0. So this proves that B of H alpha is not 0. That was the have I finished with this or there is still one more? Yeah, I'll go. 5 more minutes. Just to finish this theorem. Then I was hoping to finish this chapter, but at least just finish the theorem. Okay. So any questions before I erase this here?
This is the last one. So if there
Which both? Which are the two?
So V of H beta alpha and no, just the last one here.
Here.
The first
Ah,
one.
sorry.
That's one. Yeah, so
Yeah.
yeah, and the bracket. So both of the terms are different from 0, right?
Right.
So like, how can it be 0 then? We just said it on the.
But we don't know the signs of them, no? All we are saying that, what I'm saying that this we don't know whether it's positive or negative or not, the signs. No? We don't know. These are some numbers, we don't know.
Yeah.
But there's a sum here. So there are a lot of terms here, right? So if I write it, so this sum over n here, there is a sum over n. Right? So a lot of terms. So we can, if I separate that out, I mean we can take the first term which is V of H beta, H alpha, because this does not depend on n. No, n is only appearing there. So times the sum over n, the dimension of the G beta plus n alpha, the space G beta plus n alpha, so dimension of this space. That is one term. Plus the second term, here there is an n here, right? Of course I can take this out, so you have a B H alpha H alpha times summed over the same thing but multiplying n. So it will be the sum over n, and n times the dimension of G beta plus n alpha. Okay. Now, so this certainly is not 0. And also I know that these dimensions are non-negative integers. With also I know that dimension of G beta is certainly not 0. No? That is because we already know that beta exists. Right? So that is certainly not. So at least one of them is certainly not 0, and others, even if they are not 0, they are non-negative integers. So this quantity is a positive integer. So a positive integer times that plus this guy. Now if this was 0, then it doesn't matter whatever these numbers are. There is no way I can make this equal. The whole thing has to be equal to 0. Right? We are saying this is not 0. This is not 0. This is also not 0. No? So this quantity is certainly not 0. Then how can it be the total result is 0? This must be cancelled from that. Right? That's the point. If this was 0, then it doesn't matter whatever this value is, this will be 0. So that can never cancel. If this is not 0, then of course, I mean this quantity need not be positive, right? This could be even because n is going from minus infinity to plus. I mean, n can be negative here and can be positive there. So in other words, we are not using too much details actually. We are using some very little information from this equation so far. Right? I mean, this equation will have many more information, but we are just taking a very tiny bit of information out of it. That this is not, that whole is not 0. Okay, just now the last part, this is again a very interesting thing. I mean, the proof is very simple, not very simple, but it's a similar thing, but the conclusion is very profound. Yeah, because so far we were saying dimension of G beta plus n alpha, etc. Whether it's 1. In SU3 we know the dimension is always 1, right? Is it possible that also happens here? So that is the question. So what we are saying now is that so the third statement is dimension of G alpha space is equal to 1. That is the statement we are trying to prove. And furthermore, G n alpha is empty. Is empty for n not equal to 0 or plus or minus 1. So anything else, n equal to 2, 3, etc., these are all empty. So it's interesting, right? Because in SU3 case, we had x alpha 1, minus alpha 1, and 0. We didn't have alpha 2 alpha 1. This was not there, no? In SU3. No? But one can say, okay, maybe this is just accident because we happen to choose SU3. But what we are saying, this is generally true. There cannot be, if I have a root, 2 times that root or 3 times that root is not a root. Okay. So for this again, we go through this SU2 chains. This we call kind of chain, alpha chain. So alpha chain. But this time, we just start from x minus alpha. Okay. X minus alpha is a particular element of G minus alpha. Okay. We know that if alpha exists, minus alpha also exists. That we know because of the non-degeneracy of the Cartan killing. This we already proved in the previous statement. So certainly this is non-empty. I pick one of them, x minus alpha here. Okay. Plus, so this is again the sum of vector spaces, H alpha, I pick up just H alpha from the Cartan. Not everything, just H alpha from the Cartan. Yeah? So one-dimensional subspace of Cartan. And then I take the sum G n alpha for n now greater than or equal to 1. Okay, minus 1 has been taken here. I'm not going beyond that. I mean below that. Just starting from here. Call this as a V. Now this space is closed. This space is closed under the action of add x minus alpha, H alpha, and add x alpha. Right? Because x minus alpha, if you see when x minus alpha acts in any one of them, it takes you one step back one step back. So if it acts on G n alpha, it will take you to G n minus 1 alpha when this acts. When x minus alpha acts, right? It will subtract 1 unit of alpha, right, from the roots. So if you add x minus alpha, commutator of x minus alpha with some x n alpha is going to be something which is x of n minus 1 alpha. So this takes you one step back. Yeah. Okay. Finally, when n is equal to 1, if I apply x minus alpha, I'm going to get H alpha. This is so because we have seen already x alpha, x minus alpha is some number times H alpha. No? This we have seen already. So when it acts on the n equal to 1 case, which means G of alpha, add x minus alpha will give you some number times H alpha. It will not give you other Cartan generators. It will give you just this Cartan generator. No? Times some number. So it's this one-dimensional space. When x minus alpha acts here, it gives you back x minus alpha. But now if I look at add x minus alpha acting on that, it gives you 0. Right? Because the commutator of x minus alpha with x minus alpha is 0. It's the same element. So the commutator is 0. So add x minus alpha annihilates it. Okay. Add means that commutator. No? So therefore this that is the action of add x minus alpha. So which means x minus alpha takes a vector here and brings you back again in the same space. Doesn't take you out of that space. Okay. H alpha clearly so because these are all eigen spaces of the H alpha. So H alpha keeps you there. And x alpha just pushes you this way, right? So add x alpha acting on that gives you there. Add x alpha acting on that gives you G of alpha, and so on and so forth. So this space is again closed under the action of this SU2. So this is again a representation of this SU2. So we can add a trace of, so again for the same argument, trace of add H alpha over this space now, it should be also equal to 0. Right? You see, this is the, so we are using this SU2 things. Actually, this was one of the ways we obtained the relation between, for SU2. You remember we obtained the relation between the J, the highest weight quantum number, J, and the dimension. That's how we related by, one way of doing it was that, take the trace over J3. And that had to be 0 because that's a commutator of J plus and J minus. And that is what gave the relation between the J and the dimension. The J the spin J and the dimension. So the same thing we are doing here. Okay. So by this I mean, of course, this is a one-dimensional space, right? So any complex number times h alpha. So this is one-dimensional, that's one-dimensional, and these are whatever the dimension we don't know. So I should put here in this script. So, but on that, so we can compute the add h alpha on each space, because these are all eigenstates of add h alpha. So we can do that. So the first one gives you. So the first term just gives you, so 0 is equal to minus alpha h alpha, right? Because the eigenvalue, when h alpha acts, when h alpha acts on, add h alpha acts on that, you're going to get minus alpha evaluated at h alpha. No? So that's this formula here. And then the commutator of this with that is 0. So this eigenvalue is 0. And then the commutator of all the remaining ones. So that is going to give me alpha h alpha, n alpha h alpha, because these roots are n alpha. So n alpha acting on h alpha, summed over n, going from 1 to whatever the value is, times the dimension of the G n alpha space. Right? These are again non-negative integers. Now that's supposed to be equal to 0. So alpha h alpha is a common factor. This we already know from the previous statement that this is not 0, right? Because this is nothing else but d h alpha, which the previous part of this state theorem, we showed that this is not equal to 0. So this is not 0. I can take it as a common factor. We have minus 1 plus sum n alpha h alpha, n dg n alpha, n greater than or equal to 1. That should be equal to 0. Okay? This is not 0, so therefore this must be 0. Now this gives very, very strong conditions, right? 1, this is minus 1, these are all non-negative. N is greater than or equal to 1. And these are non-negative numbers. I know that for n equal to 1, the dimension is not 0, right? Because alpha is a root which exists. So g of alpha, at least the dimension of g of alpha is greater than or equal to 1. At least it is 1. No? Now if, and for n greater than 2, n greater than 1, so okay, already for n equal to 1, you see, n equal to 1, you get the 1 times the dimension of this. This is minus 1. So it tells you that the only way it can happen is if dimension d of g alpha is 1 and d of g n alpha equal to 0 for n greater than 1. Is that clear? This is just 1. So I want to get out of this, all of this, just 1. But each term is non-negative. No? Already from the n equal to 1, we are picking up 1 times the dimension of g alpha. Okay? The next term will be 2 times the dimension of g2 alpha, and so on and so forth. If dimension of g2 alpha is not equal to 0, then you get a factor of 2 times something, which is, that's already going to overkill it, right? Because everything else here is non-negative. So the only way I can get this to be 0 is if dimension of the g alpha is 1. Dimension of g alpha is 1, and all the others 0. That means these are not roots then, right? That's what it means. N alpha for n greater than 1 is not a root. So this implies, this is a very important conclusions we get from this. So this implies that n alpha does not belong to the delta for n greater than 2, n greater than or equal to 2 integers. But of course then, since we know that for every root there should be a negative root also, this is also true that for n less than or equal to minus 2. So this is does not exist. That's what I'm saying. Huh? And delta does not, and alpha does not exist. Furthermore, alpha and minus alpha of course belong to the delta, but the dimension of the alpha space, G alpha, and equal to dimension of G minus alpha space is equal to 1. I mean, we did it like this. You can also, I mean, from this discussion, we are only getting information about the non-negative ends, no? But you could take another V. You could start another V, which starts from X alpha. You know, X alpha plus H alpha plus V plus G minus N alpha. No, just the opposite of this. You can do the same analysis, and then you will find that only G minus alpha has one dimension and nothing else. So it's just the inverse of this, not inverse, just starting from a different vector space. So there are rather very important conclusions one is getting from very general. Okay, I think I should stop here. It's already 6 o'clock. You know, this chapter has still quite a way to go. Yeah. So the next bit, I mean, not today, but the next bit, you see that we obtained all these very interesting things that the dot product, I mean, the angles were like 60 degrees and things like that. No? We'll see that, okay, it will not only be 60 degrees, there are a few more other possibilities, but not continuous angles. No, I mean, it will be some very special angles will appear. That will be the next part in this chapter. So we'll do that. Any questions?
The last one, the dimension of G and alpha is equal to 0 for n greater than 1.
Yeah. So maybe I should just write it more clear. Just open this bracket. Open this sum. Open this sum here. So this sum. So this is okay. So we want this to be 0, right? So what is that term? First one is minus 1 plus n equal to 1. So that is 1 times dimension of G alpha plus 2 times n equal to 2 times dimension of G 2 alpha, right? Plus 3 times dimension of G 3 alpha. Okay. Now these are all non-negative numbers. So there is no way that this can be 0. This sum should be, I mean, so in other words, this whole thing should be equal to 1. Right? That's what we are saying. But there is no way, I mean, if any one of them is not 0, this is already, suppose this is equal to 1, then this is 2. Okay? And none of these guys are going to be negative. Okay? So that's not possible, right? So all of these guys are 0. And furthermore, a dimension of G alpha is 1. So that's the conclusion here. Dimension of G alpha is equal to 1, and all the other ones for n greater than 1, dimension of G alpha is 1.
Well, I was just looking at there, like 2 n alpha is increased for n different from 0.
So, sorry, repeat that again?
So from the start, so third one.
You mean this line here?
Yeah. Yes.
Yeah. Yeah, so that's why, I mean, so only for these guys is non-empty. Is non-empty. Oh. Sorry, non-empty. Yeah. Only for these are non-empty. Yeah. And empty for everything. Sorry, it's a mistake. Yeah. Okay, so if there are no more questions, then we'll stop now and we can continue tomorrow. Okay.